Okay, great. Welcome back, everybody, to the last talk session of the conference. So we'll have two talks, two slightly shorter talks, possibly, maybe. And the first one is going to be Emil Martinec telling us about ADS3CFT2. The way.
All right. Thanks to Nick and Josef for putting together a very stimulating meeting. I wish them and all the rest of us that it's next year in Paris. So today I'd like to talk about a world sheet point of view of the sorts of things that are being discussed in this conference. So I'll be making very heavy use of technology that was developed, more years ago than I care to remember, but has been undergoing steady development, much of it by Gavon and Kudasov and their collaborators, that is applicable to very topical subjects having to do with gauge gravity duality. And so, come on. So what do we want to do? We want to describe some situation where there's gauge gravity duality, but we can analyze it from the world sheet. And that kind of restricts things rather dramatically, because the world sheet formalism has a lot of difficulty dealing with Ramon flux. And so D-branes are kind of rather painful to deal with, except perturbatively. And since we're interested in some background with a large amount of this sort of flux, that restricts us to Navier-Schwarz type fluxes, so NS fibranes, fundamental strings, and momenta. And so we'll be largely looking at NS fibranes compactified on a 5 torus, where we take one of the circles of the 5 torus, denoted by the coordinate y, and take it to be large. The other directions of the 5 torus will take to be essentially of order string scale. Now, NS fibranes are closed string solitons, so they're quite heavy objects. If you like, their sort of mass is of order 1 over the coupling squared. And so their back reaction, just like something like a monopole, is some classical field configuration. And so a lot of the gravitational back reaction, if we can incorporate these objects into the description, will be automatically incorporated. Further point is that these the Navier-Schwarz fibrane is kind of a cornerstone of a lot of interesting aspects of gauge gravity duality. Just on their own, if we take a decoupling limit, they lead to something called little string theory, whose low energy limit is the 2-0 theory in 6 dimensions, but looked at some higher energy scale, the little string is an object which is, you can think of as a fractionated fundamental string, where in the presence, when dissolved into the fibranes, the fundamental string breaks up into sort of N5, where N5 is the number of fibranes, N5 strands, each of which has a tension which is of order N5 times smaller than the fundamental string tension. And so in particular, the thermal gas, the high temperature limit of such a set of fibranes will be a Hagedorn gas of these little strings rather than a Hagedorn gas of fundamental strings. And then there's a further decoupling limit one can take, where one takes the size of the circle. One takes a fundamental string winding, a large amount of fundamental string winding around S1y, and takes a limit where Ry gets large. Then the fundamental string back reaction can be macroscopic, and that will lead us to an ADS3 CFT2 background. And so our theme is going to be that the world sheet formalism sees a lot of this structure, but from a bulk point of view. And by analyzing the the observables in the worldsheet theory, we can identify the observables in the dual CFT description, and therefore form a bridge between the two. So let me begin, though, by just talking about fibranes on their own, because this leads to a lot of the intuition that undergirds the rest of this discussion when we add the fundamental string winding to go to ADS3. And so if I have a bunch of coincident fibranes and I look at the geometry in the string frame, it's just flat space for the directions that are parallel to the fibranes. And then if I write the transfer space in polar coordinates, there's an overall warp factor, which is given by some harmonic function. And there's a magnetic B field flux, field strength flux, that's basically just constant through the, well, that's related to this harmonic function. And then the dilaton, which is blowing up as we go down the fibrane throat. Okay, and so we can take a decoupling limit. The decoupling limit in this case is to get rid of the constant in the harmonic function, but that involves taking the string coupling to 0. When I say we're taking the string coupling to 0, what I mean is you have a throat which opens up onto an asymptotically flat region. In the asymptotically flat region, there's some, the string coupling saturates to some value. We take that value to 0. So in the process, what we're doing is sort of sending the top of the throat up to infinity. So the string coupling at infinity is 0. But as we come down the throat, there's of course a linearly, there's a growing dilaton. And so in the interior, deep down the throat, there's still interacting string physics. Okay. Now, when you've taken that decoupling limit and you look at the radial coordinate, it just has a metric dr over r squared. So log of r is a free field in the worldsheet sigma model. Similarly, the r squared gets canceled against the warp factor. And so the angular 3-sphere goes to a constant size. The H flux goes to a constant. And so in terms of a worldsheet sigma model, we have a sigma model on a 3-sphere with a 3-form anisymmetric tensor flux, and that's otherwise known as the SU2 Wessel-Witten model, with a level related to the amount of magnetic flux. And that total magnetic flux gets 2 contributions, one from the bosonic sigma model on the 3-sphere, and another from its worldsheet fermionic superpartners that give a contribution 2 to the total level. Okay, and one key conclusion one draws from that is that in this sort of standard Nivas-Schwarz-Ramon covariant string description, you can't have a throat of less than 2 fibranes, because that would involve a bosonic Wessel-Witten model at negative level, which is not a unitary conformal field theory. But the worldsheet, yes? Question?
Yeah, I was going to ask whether you might have a different formalism than RNS that can deal with 1 NS5.
Yes, so there's this formalism which is being developed by Gopakumar, Eberhard, and Gabradil, which I'll have a brief comment on later. But for the most part, I'll be dealing with the NSR formalism, for which this is an accurate statement.
I see. So there's nothing wrong with the NS5 brane from the worldsheet point of view. It's just that your formalism is breaking down.
It's so you can deal with a single. So what their formalism deals with is a single fibrane in the presence of a macroscopic number of fundamental strings.
I see. So if you take F1s, will their formalism still work?
Sorry?
If you just want to deal with 1 NS5 but without the F1s, would their
then I don't know of any formalism at the moment.
I see. I see. So it is not clear whether a single NS5 brane can be described in any worldsheet formalism without the F1s.
Yeah, well, the reason I say that will become clearer in a couple of slides. So if you'll hold off, I think the picture will become clear.
Thanks.
Okay. So you might say we've got a worldsheet description of the throat of a bunch of fibranes, but as usual, well, as often happens in worldsheet string theory, you can describe things which are in some sense fictions, in the sense that there is no S matrix for this system, right? Because you might try to send in something from the top of the throat, it runs down the throat, it hits strong coupling, and nothing, prevents it from, it's free field theory, right? So you send some wave packet down radially, it just keeps going radially into the strong coupling region, and you lose control over its properties. And so while there's a worldsheet conformal field theory, it kind of has no observables in it. So it's kind of a Pyrrhic victory. So then the question becomes what can we do to patch that up? And so we need some sort of infrared regulator, something that keeps strings from going to strong coupling. Okay, and there are a couple that we'll talk about. That have been the focus of the early work in this subject, and one is to regulate by dumping in a bunch of fundamental strings, as I was describing a bit earlier, and the limit then one takes is to wrap a macroscopic number of fundamental strings around this S1Y, take the decoupling limit G string to 0 that decouples the 5 branes from asymptotically flat space, and then take the further fundamental string decoupling limit that sends Ry to infinity, so that in some sense, the mass of the fundamentals, the macroscopic number of fundamental strings competes with the mass of the 5 brane in back reacting on the geometry. If one stays away from that limit, then one has is a charge radius, if you like, for the fundamental strings. And so the geometry looks something like this, where asymptotically at a radius that's larger than the charge radius of the fundamental string back reaction, one has the linear dilaton throat of the 5 branes that stabilizes at some radius Ry for the Y circle. And then once one goes inside the charge radius, one sees that the fundamental strings are back reacting on the geometry and causing that Y circle to its proper size to shrink. And so one has an ADS3 region ending with a cap in the infrared, where the value of the dilaton is a fixed scalar, which is set by the ratio of the fundamental string and 5 brane charges. And so, of course, that limiting theory is what it's ADS3, which is otherwise known as the SL2R Wess-Zumino-Witten model. The SU2 stays along for the ride, and so the worldsheet theory is exactly solvable once again. And it was also noted back in the day that one can deform back to the linear dilaton asymptotics by taking this SL2R Wess-Zumino-Witten model and adding a current deformation to the worldsheet sigma model. And that's something that can be done while maintaining the exact solvability of the worldsheet theory. And so in this theory, then you would like to reproduce what you know about the space-time CFT. And that was laid out in work of Givon, Kutuzov-Seiberg, follow-up work by Kutuzov-Seiberg, and important work on the SL2 WZW model by Maldacena and Oguri. And it turns out you can construct worldsheet vertex operators that realize the symmetries of the space-time CFT. So the first thing you'd like to check is that indeed I have some ADS3 background. Where is the current supermultiplet, the stress tensor supermultiplet of the space-time CFT? So it's constructed as a worldsheet vertex operator. What's a worldsheet vertex operator? It's some center of mass wave function in SL2R times SU2, and then decorated perhaps with some oscillator excitations. And things like gravitons have vertex operators, which are a single oscillator excitation on the left and on the right times the center of mass wave function. So we can pick the very particular mode of the graviton, sort of what's called sometimes the singleton mode, which corresponds to the holomorphic stress tensor excitation. And we can build it as a worldsheet vertex operator. And similarly for the supercurrent and the R current is just the symmetries of the S3. And so in this way, we can build worldsheet vertex operators. We can do a worldsheet a computation of the space-time OPE of those currents and verify that we reproduce the stress tensor and current operator product algebra with a central extension. That central extension is another worldsheet vertex operator. In fact, it turns out to be essentially the zero mode of the dilaton, which is this fixed scalar, which, as I mentioned earlier, measures the number of fundamental strings in the 5-brane background. And one other important point to make is that the Ramon-Ramon moduli, as I mentioned in the beginning, have to be turned off if we want to avoid pain. But this means that one is working at a singular point in the moduli space of the space-time conformal field theory. This goes back to work of Seiberg and Witten on the D1, D5 system, but it equally applies to the F1 NS5 system. And what is meant by a singular CFT? It's that above some threshold in energy, there's a continuum of what are called long string states, where you can take a fundamental string, remove it from the set of the strings in the background, and pull it off to infinity, okay, at finite cost in energy. And so there's the spectrum of the theory consists of what you might call short strings, strings that are bound to the ADS cap and have wave functions that are exponentially decaying out towards the boundary. And then there are these long string states which have some plane wave wave function in the radial direction. And so the long string states have an S matrix. That is, they basically have some radial momentum inwards. You can send them in, they'll scatter off the ADS3 cap and then come back out. And so that's, you can understand that from the point of view of the SL2R representation theory. The normalizable wave functions are the ones that are exponentially decaying or in the discrete series of SL2R representations, whereas these long strings that are scattering in and out from the boundary are continuous series representations, spectrally flowed in the SL2R representation theory. So that's theory one. What does it do for you? It's basically you're computing this. You can do a worldsheet calculation of correlators in the space-time CFT, right? So as I said, these vertex operators are in some wave functions. We can use the wave functions that represent local operators in the space-time CFT and use those to calculate basically some string version of Witten diagrams. So we're calculating essentially light operator correlators around the CFT vacuum, right? The SL2 invariant state, because we're dealing with the SL2R invariant WZW model.
So, Emil, how well is the space-time CFT picture of this singular CFT understood?
So the space-time picture is that you have some. The usual picture is you have what's called the Higgs branch of the system, where some CFT of the Higgs branch of the strings. That is, they come in to the 5-brane, they dissolve in the 5-brane as some kind of instanton or other collective excitation of the gauge theory on the 5-brane, and then there's some limit where you shrink that instanton or whatever collective excitation it is, you shrink it to 0 size and it emerges out onto the Coulomb branch. And so you can think of this long string as basically being part of the Coulomb branch of taking a 1-brane out of the system, okay? And so if your CFT is built on the Higgs branch degrees of freedom, the description of the Coulomb branch is some strong fluctuation of tiny instantons, and so it's some strongly fluctuating regime of the Higgs branch variables because they're trying to describe something which is localized on the Coulomb branch. And so that's why for them, it's a singular thing. For the worldsheet formalism, it's perfectly benign. It's just some statement that, okay, there are some representations of the current algebra which describe fundamental strings on the Coulomb branch, and so what? The worldsheet formalism is something which perfectly well captures something that is very difficult to describe from the point of view of the space-time CFT.
Right, because my question is a little bit in terms of abstract CFT, right? We're used to CFTs where I just list some operators and they have some properties. So what you mentioned sounded more like a gauge theory description of the boundary theory.
Right. Well, so that gauge theory description has of course an infrared fixed point, which is the CFT of interest. Now that CFT is rather indirectly described. So some other point in the moduli space, which is far different from the one I'm working in, there's some description in terms of some symmetric orbifold. So you have to take that description, pull it a macroscopic distance across the moduli space to the regime where we're working, and then ask the question, what is it? And one of the things that is, so there's some formal description of that as a sigma model in that regime as perhaps the conformal field theory whose target space is the moduli space of instantons in some gauge theory on T4. And that's sort of the qualitative description that it's been given, but nobody has any concrete understanding of it better than that. And furthermore, we're working on the limit of the moduli space, as I said, where this Coulomb branch opens up. If you turn on these remote moduli, which I'm resisting using, then what they do is they lift the Coulomb branch and keep strings confined to the ADS region. So precisely because we're working in a situation where there are only NS fluxes turned on, necessarily the space-time CFT is in this so-called singular regime.
Right. And sorry, maybe I shouldn't keep you more, but Kutasov keeps on talking about some different symmetric product orbifold with respect to the number of F1 brains. I guess that's not the one that you just mentioned, right?
So that's a description of the Coulomb branch as a Fock space of fundamental strings. Right. The Fock space is essentially a symmetric product structure. So if you're only interested in describing the sort of part of the configuration space, which has to do with these F1s way out on the Coulomb branch, that's described by a symmetric product. But in general, the CFT has this region deep in the middle, which is where the BTZ black holes are, which, as I was mentioning at the beginning, has more to do with these fractionated fundamental strings that are called little strings, which we know very little about because it's strong coupling physics.
I see. Okay, thank you very much.
All right. So a second infrared regulator is to work on the Coulomb branch. And so to do that, the situation that's been studied is to take the N5 fibranes and pull them all apart a little bit. And the calculable configuration is where you separate the fibranes in a ZN5 symmetric array in one particular two-dimensional plane, which we'll call the X1, X2 plane in the transfer space. So the fibrane harmonic function then just becomes a sum of individual contributions of separated fibranes. And the interesting thing is that because there's no, I argue that there's no description of an isolated fibrane throat, then something funny must happen as I'm coming down this throat and I reach the scale of the size of this radial separation of the fibranes. Because, farther up, the probe will see some average of all the fibranes together, but when it gets close enough, it should start resolving individual fibranes. But if there's no worldsheet description of an individual fibrane throat, something has to happen. And what happens is that the fibranes are repelled before they get close enough to resolve the fibranes, for reasons that I'll describe in a minute. So, but rather surprisingly, the worldsheet dynamics continues to be an exactly solvable conformal field theory on the worldsheet, as I'll describe in a minute, as I'll describe now. So the way to think about this is to think about the linear dilaton of the radial direction as itself coming from another Wessamino-Witten model. And the Wessamino-Witten model is the SL2R model, but where we gauge the Borel subgroup. Borel subgroup is just the group of upper triangular matrices with the identity on the diagonal. And so if you do that, you basically remove 2 dimensions from SL2R by the gauging. What's remaining is the radial direction. The radial direction has a linear dilaton after the gauging, and it precisely describes what we had before in the CHS model. But the Borel subgroup is generated by a null current within SL2R. And then the game we can start playing is to change the embedding of this null current and have it not just in SL2R, but also put it in SU2. And so the thing to do is to switch to a new gauging where we gauge a null linear combination of SL2 and SU2 currents. And then to do that, so that'll do a bunch of things. Okay. One thing it will do is it'll break the angular SU2 isometry. So we're definitely doing something that breaks the angular symmetry. And furthermore, in the gauging, it'll change sort of where the singularity is. Okay. The singularity where the dilaton blows up. Okay. Before, the dilaton blew up at r equals 0. Now it's going to blow up somewhere else. Where does it blow up? Well, in the gauging, there's a quadratic term in the gauging, just for gauge invariance. And it has a coefficient which depends on the radial coordinate in ADS3 and in the polar coordinate on S3. And where this vanishes, so if you integrate the gauge field, which just appears algebraically, you'll get some effective geometry, which looks like this. It is the geometry of a bunch of separated fibranes separated on a circle, written in some funny coordinates, where this ring singularity, where the fibranes, if you just smeared the fibrane source over this ring, it would yield this geometry. So what supergravity sees is some kind of smeared version of the Coulomb branch geometry, where indeed the locus of the singularity, where, for instance, the dilaton blows up, is rho equals 0 and theta equals pi over 2. And that's indeed a circle. It's the circle that's parametrized by one of the Euler angles on S3, which I've called phi. Okay. So you would conclude naively that there's still a singularity where the dilaton is blowing up, if you were a supergravity person. But if you're a string theory person, you say, that can't be right. This is some ordinary nonlinear sigma model on SL2 times SU2, which itself has no singularity anywhere. And all we've done in the gauging is we've projected the observables of those 2 sigma models onto a subset, which is invariant under the gauging. So if we take a non-singular set of correlators and we project them onto some singlets under some isometry group, they can't possibly be singular. And so what's happening? Well, what's happening is that non-perturbative effects in the sigma model come to the rescue. What I wrote down here was the classical sigma model, and we should really ask about what are the effects that are non-perturbative in alpha prime. And it turns out that what you might have thought was a bunch of individual fibrane throats that you could probe. If you're a gravitational person, there is no alpha prime, and so you would just say, oh, it's a geometry, and I can go arbitrarily far down this throat and find strong coupling. But in fact, in string theory, this is not what happens. Near the source, there is an exponential Liouville-like wall that prevents strings from reaching strong coupling. And so how does that work? Well, there's a known duality of the SL2R Wessamino-Witten, or the quotient that we're dealing with, SL2R mod U1, to an n equals 2 Liouville theory. It's just an exact equivalence of conformal field theories. And similarly, for the coset of SU2 by U1, that's equivalent to an n equals 2 Landau-Ginzburg model with a superpotential z to the n5. Liouville theory, n equals 2 Liouville theory is just a sigma model with flat kinetic term and an exponential complex exponential potential, superpotential. And so, so this geometry, which is the geometry of our coset, is itself quantum equivalent to some kind of superpotential. And if you look at the superpotential and factorize it, you note that the zeros of the superpotential are at the n-fifth roots of unity, which is exactly where the fibranes are. So this exact worldsheet quantum duality knows something about the discrete fibrane sources and not just their average smeared locations. And ultimately where this comes from, at least the SL2R part of it, is from an isomorphism within SL2R representation, affine representation theory that says that a discrete series, a minus discrete series representation with some spin J and zero spectral flow is completely equivalent to its conjugate representation, but with a conjugate value of the spin and a winding number -1. And so what that says is that there's sort of one single background as far as strings are concerned, and it kind of has two aspects to it. It has a gravity aspect to it, which is the SL2R mod U1 geometry. And then it comes inextricably linked to a string winding condensate, which is exponentially confined to the cap in the geometry. So there's sort of two pieces, two branches, if you like, to the wave function of this single background object, one of which is a string that's winding and trying to crawl up the cigar geometry, and the other, which is just a localized graviton, which is trying to propagate around the geometry. Okay. David talked about D-branes, and as I see I'm kind of running short on time, let me skip that and come to the heart of the matter, which is that that's all very well and good, but so far we're just describing ground states as backgrounds in the worldsheet to the worldsheet theory. And what strings worldsheet theory is going to do is it's going to compute for you some perturbative excitations around that background. Now that's not very helpful if we're interested in black hole physics, where we're interested in states that are very far from the vacuum. And so we need to do something in order to start describing things that are relevant to the topic of this conference. And so that thing to do is to change once again the embedding of the gauge group in the target space Wess-Witten model. And so remember that for the fibrane, there were these longitudinal directions to the fibrane. The Coulomb branch was described by taking SL2R times SU2 and getting rid of 2 dimensions using some kind of gauge projection. And so far, then the gauge projection was only projecting in SL2R times SU2. But there are all the other directions of the target space, namely R51 or R time times S1 times T4. And we can embed the gauging partly in those other directions, which are longitudinal to the fibrane. And so if we gauge project some admixture of SL2R times SU2 and RT times S1Y, then the projected geometry will, the sort of physical geometry that's unprojected will be some admixture of those two. And it turns out that when you do that, if you take a linear combination of currents which are null in SL2R times SU2 and separately null in RT cross S1Y, and you gauge project on that, then the geometry is, as advertised, a linear dilaton for large radius. Radius is still basically the radial direction in SL2. And so if you work through the geometry of what the gauge orbits look like that are being projected away, those gauge orbits are the space that's transverse to the gauge orbits is mostly ADS3-like at small radius, and it's mostly RT cross S1Y-like at large radius. So you precisely get a projected geometry, which is the one advertised. It's ADS3-like in the cap, and then it rolls over at some radius, which is governed by the size of the circle, S1y, that the fibranes are wrapping, to some linear dilaton fibrane throat at large radius. And so what do we get this way? We get, if we take this, there's a discrete parameter K in the gauging, which is basically describing how many fibrane strands do you hop over before you periodically identify. So if you make that parameter 1, you get the maximally spinning state on the BPS line. And as you increase K, you get discretely K equals 2, 3, 4, et cetera. You're decreasing the angular momentum of a BPS, 2-charge BPS state by a factor K. So these are precisely the circular Luhnen-Motor supertube profiles, but realized in a fully stringy manner. And as David described in his talk earlier in the week, David Turton, there are other embeddings. You can then, after you've started playing this game, you can ask what's the most general embedding of a null current in the target sigma model. And it turns out if you analyze the possibilities, you realize also states that are spectrally flowed or fractionally spectrally flowed, starting from one of these 2-charge geometries, or indeed also the J-Mart geometries, the non-supersymmetric J-Mart geometries that were investigated starting about 15 years ago. So, so then you can ask, okay, if I can describe those, what do perturbations around them look like? And one thing you might be interested in are what are the half BPS perturbations of these half BPS supertubes. And so the general supertube, I think this was written a number of times in earlier talks, looks like a geometry of this sort, where once again, the metric coefficients are harmonic functions and forms. But in the nice aspect of the Luhnen-Motor construction is that those harmonic forms are explicitly given in terms of some Green's function integrals of a source profile F, which is basically where the fibranes are. We've separated a bunch of fibranes. I should have said, we start with the Coulomb branch geometry, that's this null gauging. And then by adding a small admixture of this, what we're doing to the source is we're basically tilting it in the way I've described, where the fibranes spiral around and then periodically identify. And so, so this gauging procedure basically directly ties the sort of Coulomb branch geometry, slightly tilted, to the source, the geometry in spacetime that's being sourced by that 5-brane profile. And so what you'll do if you start computing now, half BPS perturbations by adding some half BPS vertex operators is you'll start wiggling that supertube profile a little bit away from this nice circular one. And okay, so the first question you can ask is, what have we done to this FZZ dual description that I was describing a bit earlier? When we go from the Coulomb branch of fibranes that are just static and sitting somewhere in the transverse space in some circle, what do we do to the FZZ dual description when we tilt things over and get this spirally source? And the answer is you just introduce some spiral element in the superpotential, so that if we replace the Landau-Ginzburg superpotential by an exponential of t plus y with some slope k over n5, what you're doing is you're basically adiabatically rotating as you go up the v direction where the zeros are. But remember, what I said was that where the zeros are is where the fibranes are. And so as you go up the v direction, this is now adiabatically rotating in the circle where the zeros are. And so you're exactly reproducing in the worldsheet superpotential of the FZZ dual description of this geometry, the source profile of Luhnen-Motor. And if you now start wiggling that profile by adding vertex operators to the background, you start going towards the more generic two-charge supertube. So, you can, of course, everything in this system at the round supertube is just SL2R times SU2 representation theory. So you can write down the vertex operators both in the FZZ dual description as a superpotential deformation or as a geometric vertex operator that deforms the geometry. And those two are the same thing. They're two different equivalent descriptions of the same object. And so you can start, wiggling the profile, and what you'll find is a deformed superpotential, perturbatively away from the round supertube, where you now start getting more generic, basically where the zeros are codes this generic Lunan-Matur profile, at least in small perturbations around the round configuration. So, carried to some extreme, if we actually condense those vertex operators macroscopically, we'll get to the generic profile. And we're guaranteed, because we're taking an n equals 2 or 4 conformal field theory on the world sheet, and we're just deforming it marginally by some superpotential perturbation, we're guaranteed that we're continuing to have an exact conformal field theory, even if we can't solve it. And then we can ask, so I see I'm running close on time. I've got a few more slides, but I think I can speed up. Is that all right, Daniel?
Fine with me, yeah. We've got a few more minutes, go a little over time. So.
Yeah. So what is this? So we can ask then question of, where are there potential singularities that develop in these two-charge geometries? And from the geometrical side, we could ask the question, what happens when this wiggly supertube profile self-intersects? Okay. And remember, the reason we should be interested in that is that we said that there was no perturbative string description of a single five-brain throat, but as soon as we have two or more five-brain descriptions, two or more five brains coincident, then there's a throat that can be described in perturbative string theory. And so you could worry that when the five-brain profile self-intersects, that you're essentially unhiggsing the five brains, going from their Coulomb branch to some kind of non-abelian little string physics. And so we should look for what that little string physics looks like in the geometrical description. And the way it appears is that in the Lunan-Matur construction, the source profile f of v is codes the location of a KK monopole core in the F1NS5 geometry. And so if you have a pair of such sources, then there's a homological S2, which is basically the interval between them together with the fibered circle of the KK monopole. And as the source contours start to self-intersect, that S2 shrinks. And if they actually do intersect, there's a vanishing cycle. And we're used to the situation that happening in string theory. What happens when that occurs in string theory is that the D brains that wrap that homology cycle become light and can condense. And so what is that condensation process here? It's basically, if we're in type 2B string theory, we can wrap a D3 brain around that vanishing cycle. Since the size of the cycle is going to zero, the tension is becoming light, or getting as light as you like. And so, but there's a remaining leg of the D3 brain. And since the cycle is sort of pinned to where the five brains are, the only thing that the remaining leg of the D3 brain can do is to wiggle in the other directions along the five brain, the T4. So when the profile self-intersects, little string physics reappears, at least some SU2 version of it, or if there are triple intersections, et cetera, some higher SUN subgroup of the little string dynamics gets restored. And so that's how it looks in the geometrical picture. But as I tried to emphasize, the geometrical picture is kind of breaking down near the source. So to confirm that intuition, we should look and see what's happening in the Landau-Ginzburg picture. And there we see more or less the same thing, that in the Landau-Ginzburg picture, two fibranes coinciding is two zeros of the superpotential colliding. But if two zeros of the superpotential collide, then both the superpotential and its gradient are zero. And that's a situation in which the superpotential is degenerating. And if you say, okay, what does that mean for the worldsheet dynamics? It means that the bosonic potential has a flat direction. Right? The gradient of the superpotential squared is flat along some direction in field space. And in that, so what's happening is basically there was this exponential Liouville wall that was keeping strings from exploring strong coupling. And the coefficient in front of that exponential, the coefficient mu, of some like, Liouville like superpotential, the coefficient mu is proportional to the separation of the zeros. And so as the zeros collide, the Liouville wall recedes, but the Liouville wall was the thing that was protecting you from hitting strong coupling. And then the limit when the zeros actually coincide, the wall recedes to infinity and a long throat develops at the bottom of which there's strong coupling physics. So the two dual descriptions describe the same physics, telling you that your string perturbation theory is breaking down precisely because you're restoring some non-abelian aspects of little string theory.
Sorry, Emil, can I ask a question, a very quick one, and also a very basic one, if I may ask?
Sure.
On the previous slide, here you're saying that the string perturbation theory is breaking down because you enter the strong coupling region. But my question is, how is this related to little string theory physics? Because we have seen at the beginning that little string theory is actually the G string going to zero limit of the theory on the NS5 branes. So we are still keeping G string to be very small. But at the same time, here we're saying that when the string perturbation theory breaks down, little string theory physics kicks in. So in one sense, you're saying there is a strong coupling region, but at the same time, little string physics is related to G string going to zero. So I'm a bit puzzled by this.
Yeah. So I tried to say this, that what's happening is that asymptotic value of G string is going to zero. So G string at infinity in the limit is zero, but the background has a linear dilaton. So it starts at infinity at the top of the throat. The dilaton starts off at zero string coupling at the top of the throat, but it's rising as you go down the throat. You go far enough down the throat, the coupling is finite. Okay, if the cap in the geometry, the wall, the Liouville wall, happens at a small enough value of G string down the throat, then the physics is still manageably perturbative. But in this one corner of the field space, what's happening is that the throat is continuing, and it can continue as the fibranes approach one another, it continues all the way down into a strong coupling region.
I see. It's kind of if I take a fiducial G string in this decoupling limit of the NS5 branes, then there's still a non-trivial G string that increases because of the running of the dilaton.
Yeah. So what's happening is there's some story that's kind of standard in these sort of situations where there's an exponential wall. So there's sort of like Liouville wall. Okay. And there's some linear dilaton. So there's some space-time dilaton, which is some Q times rho, where rho is this radial direction. Okay. And so, yeah. And so, so G string local is e to the phi.
Okay, got it. Yes.
And so the linear dilaton is the thing that makes it work. So out here at rho goes to infinity, the coupling goes to zero. That's the decoupling limit that I was talking about. But as you go down the throat, the coupling increases, and unless you do something to stop it, there is no perturbative dynamics.
I see.
In the infrared.
Thank you very much. Indeed. Thanks. Thank you very much.
Okay. So that leads me to believe, and I'll have words to say if I'm allowed in the scrambling panel. I think this leads to a rather interesting picture of what's the scrambling dynamics once you add some non-extremality and let there be some kind of dynamics on this half BPS moduli space. But let me defer that to later. Just to set the stage then for what Bruno's going to say. So I fervently believe that the thing that's going to explain the bulk of the black hole entropy is this Hagedorn entropy of the little strings that are the restored non-abelian dynamics. And that's in line with everything we know from other contexts of gauge gravity duality, where we should think of the formation of black holes as being some kind of deconfinement transition in the underlying gauge theory. And so here the underlying gauge theory excitations are the little strings, and they're in some sense being deconfined precisely when you have one of these crossings. And so the picture I have is that the cap geometries are some kind of Coulomb branch coherent states, and that the real black hole physics that we need to focus on is trying to understand the little string excitations. But as I say, let me defer that, the detailed discussion of that to the panel. But to set the stage for what Bruno's going to say, we can sort of provide a backdoor probe of that picture by asking what happens if we remove the T4 from the target space, just by hand. Okay, the little string excitations and what I described are the place the little string can wiggle is the space that's along the 5 brane at this intersection point, and that's the T4. So if we remove the T4, we sort of remove all the phase space for the little strings to wiggle. And so you might think that, well, maybe the phase space for little strings is not so important, and that the perturbative string dynamics is okay. And indeed, that turns out to be the case. There's a phase transition so as you sort of move around in the space of potential compactifications for the manifolds that the 5 brane can be compactified on. One thing you can do is to wrap it on some vanishing cycle of a Calabi-Yau fourfold. And in that case, it turns out the correct worldsheet theory has no T4. And if you work out the worldsheet balance, you find that the level of the Wess-Zumino-Witten model is n over n plus 1, where n is the number of 5 branes. And so this is k less than 1. And so but k is the radius of the ADS relative to the string scale. So in the process of eliminating the T4, the ADS becomes completely stringy. But because we have a non-perturbative alpha prime description, that's okay. We can still, make progress. And so what Bruno is going to describe is this sort of stringy regime where the Higgs branch excitations of little string are suppressed. And as was argued by these gentlemen, in that regime, there are no BTZ black holes. The BTZ solution is not a normalizable state in the Hilbert space. And so I believe that's related to the dearth of Higgs branch excitations in this situation. That's, well, let me leave that to Bruno to describe in detail. There are various other generalizations. Once you started playing this game, various other Landau-Ginzburg models, various other Wess-Zumino cosets. So there's some, landscape, if you like, of things that are describable by worldsheet string theory. But I hope I've convinced you that there's that landscape isn't just light excitations around some ground state of some CFT2 in space-time, but actually a much richer set of things, including many of the sorts of things that people like to describe as having to do with black hole or near black hole physics in this system. And so let me just comment briefly on this model that Monica asked about. There is a description.
Sorry, Emil, do you have a lot of slides left? Okay.
This is it. Right. Yeah. So let me just comment on that and then shut up. So there is a description of n5 equals 1, but with a macroscopic number of fundamental strings piled onto it. That's been the subject of a number of investigations by Eberhard et al. And so how does that fit into what I was saying? Because I said there was no description of the throat of a single 5 brane. Well, if you look at the SL2R representation theory of that model, it has basically a single representation. And it's just the J equals a half representation. That's sort of the borderline between the discrete series and the continuous series. And that, so because there's only one representation, and if you look at the wave function of that representation, it's basically concentrated near the boundary. In their calculations, they find that the wave function of the perturbative strings are essentially concentrated out at the ADS boundary. So I think that fits into what I was saying, that the strings are kind of pinned at the ADS boundary, and there's no local description of the interior of ADS. Because basically what they're describing, as claimed by them, is basically reproduces the correlators of the symmetric product T4. And so it's the description of the bulk as some very indirect collective excitation in that theory. But let me not say more about that. And just throw up my conclusion slide and leave minus 10 minutes for questions.
Okay, thanks, Emil. Thanks. I don't clap, I give clap emojis. So thanks for that great talk. We already had a lot of questions, but you know, if there are any more questions at the end here.
I put a hand up, but
yeah, put a hand up. I can't really see.
No,
I
that.
cannot put a hand up, but I had a question. If
no, but I put up a hand up, and I do have a question. So let me jump in first, and then.
okay.
So I'm sure it was bait for me, but on about 3 slides back, there was there was a question: are there stringy superstrata? And the answer was yes. What the hell is that?
You're referring to this?
Yes, I saw that go by at the very bottom, and I thought, there's
Yeah,
bait for me.
so, right. So, in the preliminary work laying out the sort of structure of these non-critical backgrounds that I did with Daniel Brennan, a postdoc at Chicago, a little while ago, we basically repeated the construction that we did with Masai and Turton for the supertubes in these non-critical models. And so it works basically the same way. So there's some supertube-like backgrounds. They're basically the analogs of the round supertubes in this non-critical theory, okay? And then there are the half BPS deformations of those round supertubes along the lines that I was describing. And so then you can ask, okay, are there analogs of superstrata? Well, the wiggly supertubes are what you get when you take the round one and you condense some half BPS vertex operators. But you could imagine condensing some quarter BPS vertex operators. And and some of those quarter BPS, so the generic quarter BPS vertex operator is stringy. It's right, some supersymmetric ground state on the right, and some generic excited string state on the left. But some of those quarter BPS vertex operators are themselves supergravity modes. And so the suggestion is that if you condense those, you'll be describing some, in a worldsheet formalism, at least perturbatively, some aspects of what you would call a superstratum.
Right.
And this was the thing that David Turton in his talk said was the high on our shopping list, as he called it.
Okay, thank you. I'll let Joseph have a go now.
I had a question about this Higgs-Coulomb distinction. So in the two-charge system, we know very well that, you have a two-charge system, and, we know very well that, all the Higgs branch states of the D1D5 system, for example, they appear as, big fat configurations with a large transverse size, even if in the D1D5, even from the perspective of a D1, of the D5, the D1s are like, some internal soliton. When you go to supergravity, when you turn on the string coupling, these become big fat configurations. So I'm just wondering why, I'm just wondering why would supertubes, for example, be Coulomb branch? I know you get them as Coulomb branch by doing all these tricks about rotation and so on, but we know that in the D1D5 system, they are Higgs branch. So why would you call them Coulomb branch?
So I call them Coulomb branch because the 5 branes are all separated in the transverse space by some small amount. Okay. So what's the structure of the supertube? It's basically, as I described it, it's that you take a bunch of 5 branes, you pull them out, separate them. So the round supertube was you first separate the fibranes out onto
Yes,
the
and then you
Coulomb
twist.
branch, and then you twist. Okay, but the starting point is a bunch of fibranes on the Coulomb branch.
Indeed.
And in the
But
twisting, you keep them separated on the Coulomb branch.
But they are joining. They became a single brain now.
Yes, but they're never touching. They're never any place where two fibranes touch one another.
Indeed, but still we know that this is the dual of in the Duality 5. We know that these beasts are the dual of the Higgs branch states. We know that, all the LLM geometries and all the Lunimato geometries, we know that they are dual to the Higgs branch states. They are the ones which count.
So they're perfectly well. So you're in some kind of gray area where I agree in the space-time CFT, in a non-singular space-time CFT, this is just some half BPS state. And you're describing it within what you would call the conformal space-time conformal field theory of the Higgs branch. Okay. Mm-hmm. But it's a state within that conformal field theory which has a Coulomb branch-like character in the sense that there are no non-abelian excitations of the fibranes. You can abelianize everything, and all the collective modes around that configuration mm-hmm. are things that exist within supergravity. And so this distinction that I'm drawing of sort of like Higgs versus Coulomb is roughly speaking that you've sort of masked up the little strings, the non-abelian little strings. When you separate the fibranes, you make the non-abelian little strings heavy. Okay, so the little string physics is suppressed by separating the fibranes, and exactly when you push the fibranes back together, those are the things that are unsuppressed. And so that I believe is the analog of the Hawking-Page transition, where the non-abelian excitations which are dominating the black hole phase get liberated.
But I think in the system, there's a clear enhancement of the degrees of freedom. When you do this twist, for example, the supertube starts having n1 and 5 degrees of freedom. The dimension of the moduli space, when you had a bunch of NS fibranes, they have a dimension, a moduli space dimension of size, 6 or I don't know, 4 times n1, 4 times n5. And now, because you are twisting them, the moduli space dimension becomes over the n1 and 5. So, there's a huge growth of the moduli space dimension. And this is why you can actually capture the Higgs branch entropy with these beasts. These beasts are capturing all the entropy of the system, including the Higgs branch entropy.
No, they don't. So, we can, we have everything at our hands, right? Mm-hmm. We just take, the spectrum of SL2R times SU2 times, RT times T4. You just take that conformal field theory, we work out all the vertex operator spectrum. And you see that in the set of things that are describable in supergravity, you're sort of missing a factor of N5 in the entropy.
Oh, but
it's this fractionation by N5 that's missing.
But that's because of this construction.
And it's the fractionation by N5 which comes when you go to the little strings.
Yes, but the only thing which is saying is that this description doesn't capture all the black hole degrees of freedom, but the supertubes do capture all the degrees of freedom of the two charges.
But I just told you I can get all the supertubes by taking the round one and deforming it by condensing string vertex operators.
Yes, but then you should get entropy.
And nothing happens that violates my understanding of perturbative string theory until I come to this place where the supertube profile self-intersects.
Sure. The intersection, I don't care about the self-intersection, but okay, what I knew and the dogma from from Samir, from the Lunimato work, and is that the two-charge system, the entropy is captured by the supertubes. I'm just wondering, why are you saying that it's not? I don't know. I'm confused.
Oh, the supertube entropy, yes, that's just the half BPS moduli space. That was counted long ago, and as I said, there's a perfect match between the half BPS vertex operators and the supertube deformation. So that's all perfectly well understood. But that's not going to get you. That's not going to get you. That's going to get you N1 and 5. It's not going to get you N1, N5, NP.
Sure. No, my objection was that there, for example, the supertubes we are discussing are Higgs branch. They are, and from your perspective, you're building them in the same way. As you take some NS5, you shift it, and you get a two-charge system by doing this shift. So it appears to be Coulomb branch construction-wise, but entropy-wise, it is Higgs branch. So that's why, but again, I have this objection. I mean, just because something looks big in supergravity, has a size, doesn't mean it's Coulomb branch. And there's another example of this, actually, if you look at the D4 brane confining theory. If you want to do in the D4 brane confining theory, there's a brane polarization due to the confining phase when the D4 branes puff up into NS5 branes. And the states there in the confining vacuum are obtained in exactly the same way. You basically uplift to M theory, you do a Melvin twist, and then you bring it back. And you get all this brane polarization of D4 branes into NS5 branes. This is a strongly coupled system, and you are capturing the Higgs branch and the confining phase of the system by looking at this D4 NS5 configurations. Exactly, the construction is identical to the one you did. So that's what I'm saying. Just because something looks construction-wise to be Coulomb branch, it doesn't need to be Coulomb branch from the field theory side.
So, sorry, could we maybe continue this over?
We have the discussion afterwards, yeah.
After the discussion, yeah. There was one more question that I wanted to get in because he had his hand up the whole time before we take a break, if that's okay. Davide has his hand up.
Cool, thanks. I have a list of 3 questions, but I guess I can just ask one of them because of time.
The most pertinent one, yeah.
Yeah, indeed. About
the other 2 in the chat, and I'll answer them there.
Okay, great, thanks. And about the Landau input superpotential here that is also shown in this slide, I think this was done for 2-charge system, right? So the Walsh superpotential is describing what happened in the physics of 2-charge systems. Is that correct?
Yes.
Oh, so do you have any idea about what happens in the case of, the most general case, which is J-mark in this model? So what happens if there is a marginal deformation that equivalently, I mean, the physics I expect should be the same, right? You still have not reaching the strong coupling region also in this 3-charge system, but if you have any idea how the superpotential could look like?
That's a good question. So
first of all, if it's useful to do so.
Yeah, so I should say that what we're doing is we're describing the worldsheet theory in a sort of manifestly n equals 2 worldsheet formalism. So we can talk about this n equals 2 superpotential. So it would basically be a question. My worry would be whether the deformation you do to go to J is something that you could describe as a superpotential deformation. So the superpotential, I should say, the superpotential deformations are sort of a limited set. It's where I'm moving the fibrines around in this 1-2 plane, and the corresponding deformation on the S3. And so if you're requiring, this is, I think, maybe the point. If you're requiring a rotation in the orthogonal 2 plane, which is what JMART is, it turns on both Euler angle rotations in the S3, then you're moving outside of that superpotential deformation, because the rotation deformation isn't just in the plane of one Euler angle; it's in the plane of both. So it may be a deformation that could be controlled on the worldsheet, but it would be more than just deforming the superpotential. So another example of that was the sort of things that Masaki was talking about, which in my language would be twisted chiral deformations of the worldsheet theory, rather than chiral deformations. There again, you've got this sort of like spirally profile around a torus, and once it's outside the 1-2 plane, it needs to turn on things that are half BPS but not purely superpotential deformations.
Okay.
Yeah, we should really break at least for 15 minutes. So let's thank Emil again. Thanks for taking all those questions too.